Alright guys, almost done. We're going to start our next lesson into circles, particularly lines and segments that intersect these circles. So before we begin, let's go over some definitions. So most of you should already know what a radius diameter is, which is identified here. Now a chord, you can see, is a segment whose endpoints are on a circle. A chord is right here. It does not go through the center of the circle, because if it went through the center, it would be called the diameter. Now a secant line is similar to a chord, however, it is not a segment, but a line. And it will go on forever. Again, this cannot go through the diameter, or excuse me, it cannot go through the center, because if it did, it would be considered the diameter, or part of the radius. A point of tangency for a tangent line is as you see here. So a tangent line passes through a circle, or alongside a circle, and only touches it at one spot, just like this. So if you were to zoom in very, very, very closely, you will see that this one line just grazes on that circle at this point, called the point of tangency, as you can also see down here. Now we're going to be using these terms often into this lesson, so make sure you take the time, write this down, and let's get started. Here, now I'd like you to try, based on the definitions, tell whether the lines, rays, or segments is best described as a radius, chord, diameter, secant, or tangent of the circle C. So take the time to do that now, and check back with me in a bit. Great. So what you should have saw is that AC, line segment AC, is my radius, right? Because it is half the diameter. Line segment AB is, since it goes through the center of my circle and is a line segment or a chord, it is my diameter. Now, line DE is a tangent. Why? Because it has a point of tangency at point B, as you can see right there. And line AE is my secant, because it goes through the circle at two different points. Great, let's continue. So here we have coplanar circles and common tangents. Take the time to write this down and meet back with me in a bit. Okay, in a plane, two circles can intersect in 2 points, 1 point or no points. Here on the bottom left, you can see that I have 2 points of intersection. In red, you'll see that I have 1 point of intersection for both of these circles. And when this happens, that means that I have tangent circles, because I have a tangent line that grazes both the small and the large circles on both of these diagrams. Here you can see that I don't have any common tangents because I don't have anything that intersect. If I were to draw a line, bad line, right there, we can see that it's tangent to 1, but there is no intersection on any of these. So let's go over common tangents in our next example. Common tangents. You're going to see that I'm going to use blue to indicate common external tangents and red to indicate common internal tangents. Looking at A, you will see that I have my external tangents. I have a point of tangency here and there. These are external for obvious reasons. They lie on the outside of my circle. Now taking a look at my Internal tangents, for obvious reasons, we can see that I have a point of tangency there on both circles and here. Here I have 4 total tangent lines, 2 internal and 2 external. How many do I have for B? Do I have any internal? How many external? If you said 2 external and 1 internal, absolutely right. You can see here. Now let's take a look at C. Do I have any internal? How about any external common tangents? Great. You should have noticed that I only have 2 external. Since I'm crossing, I cannot draw a tangent line for both of these. Let's move on. Oh, that came in a little late. But you can see here now. Now I'd like you to try. Tell how many common tangents the circles have and draw them. For you, you won't have to draw them. You'll see it on your screen. State whether the tangents are external tangents or internal tangents. Give it a shot now. Great. So you should have seen that these 2 circles have 2 internal, 2 external. Here we only have 1 external, and here I have none. Let's move on. Okay. Tangent lines to circle theorem and external tangent congruent theorem. Write these both down because we're going to be using these in our next example. Okay, so if I have a tangent line, M, that means that it is perpendicular to the radius. And hopefully you remember, if it's perpendicular, then it creates a right angle. That is very important, that you'll see soon. External tangent congruence theorem states that if I have 2 common tangents from, say, point S, then line segment RS is congruent to line segment TS. And therefore, those segments are equal. So, let's take a look at our first theorem and application. I want to know whether line segment TST is tangent to the circle P. So, this is the line segment in question. And well, if you remember the theorem, if not, take a look at your notes. You know that if, in fact, ST is tangent, that would make these 2 lines perpendicular, making this a 90-degree angle. And if it's a 90-degree angle, notice that we have triangles. Remember what we did in 9.1 and 9.2. We can use the converse theorem in this case to figure out whether it is a right triangle. So I'm going to use the Pythagorean theorem here. 12 squared is equal to 35 squared is equal to 37 squared. And you will see that you will get 1369 is equal to 1369. So yes, because it satisfies our Pythagorean theorem, ST is perpendicular to PT. So line segment ST is perpendicular to the radius, hence it is a tangent to the line, or excuse me, tangent to the circle. Hopefully you got that. Let's take a look at the next theorem. Oh, just kidding. Let's do one more example. Here we have a diagram. Point B is a point of tangency. That's very important. This is a point of tangency, which means let's keep the colors consistent, which means that line segment AB is a tangent line. If it's a tangent line, then angle B is 90 degrees. Very, very important. Now my hypotenuse, if you don't automatically see it, is opposite to the right angle. So the hypotenuse is 50 plus r. So exactly what I just said. And here we have AC squared plus BC squared plus AB squared to satisfy my Pythagorean theorem using the line segments. Substituting the values here, you'll see r plus 50 squared, the hypotenuse, is equal to r squared plus 80 squared. Solving for r, remember, it's r plus 50 times r plus 50. And then we're going to use the FOIL method to get to the next statement you see below. Now, simplifying for r, you'll get this, then you will divide by 100 on both sides, and you will see that the radius is 39 feet. Feet, because these are our units of measure. Let's move on. Okay, now here is the next theorem. Refer back to your notes, take a look at it. Now let's get going. RS is tangent to circle C at S. And RT is tangent to circle C at T. So, if you can recall the external tangent congruence theorem, that states that line segment RS is congruent to line segment RT. So, using algebra, I'm going to substitute and solve for x and get x is equal to 8. All right. Now I'd like you to try. Is DE tangent to circle C? For number 7, ST is tangent to circle Q. I'd like you to find the radius of that circle. And points M and N are points of tangency. Find the value of x. Do that now. All right. So hopefully you said yes, because you saw that that was 90 degrees and it worked. R is equal to 7. Because ST is tangent, you know that this is 90 degrees, and then you can use the Pythagorean theorem to solve like we did in the previous example. Points M and N are points of tangency. That is also important because you know that these are tangent and they're coming from a same point. So r squared is equal to 9. Take the square root of both sides, plus or minus 3 for x. And that's it. That satisfies everything we're doing for this one small section. This is just our introduction. We will get into circles a little bit deeper in the coming weeks. Hope that was informative. Good luck.